Well, hello everybody and welcome back. We're going to be looking today at some equations that help us kind of predict where objects will be in terms of their projectile flight path. Some kind of specialized equations, you might say. We've been using kinematics equations and talking about where an object is in the x direction and the y direction when it's in some sort of projectile flight. But these equations are going to be more specialized, you might say. If you've ever played Angry Birds, for example, you probably know that there are certain angles at which you can get your bird projectile to go either very far or less far, depending on how you angle it. And that's what some of these equations are going to prove to us. They're going to prove to us today. So the first of which is called the trajectory equation. And what this does is it tells us where an object will be in the x direction, say right here, it'll tell us where it's going to be in the y direction, given an x direction and some other information about it. It says in the notes that it's usually less helpful than other equations, and that's true because it's very specific. But if we know a few specific things about the motion of the projectile, for example, if we know its initial velocity right there, and if we know the angle being theta, and of course g always being g, or the acceleration of gravity, what this really tells us is that we should be able to determine what y will be, or that is what the y location will be for any position of x. So if we know where it is in the x position, it will return to us where it will be in the y position at that very point in time, without actually knowing time. So this is how we break it down. We actually take time out of the equation entirely. We look at let's go to the x part right up here. We look at an equation we're used to. Displacement is the velocity initial in the x direction times time, and we solve for t. We can take our initial velocity in the x direction and break it down into initial velocity total times the cosine of theta. That's really the same thing as initial velocity in the x direction, and we solve this for t. All right, so we have something in terms of time right here, and then we look at the y component. Well, when we've been doing our kinematics equations with free fall objects and projectile motion, this right here is an equation we're used to using. That is, our displacement is initial velocity in the y direction times time, plus, well, we've been doing plus 1/2 at squared, but you can write minus 1/2 gt squared. It's the same thing. But again, what we do here is we take this time here. We take this, and that is what all this is equal to. All this is equal to time. We take it and we drop it into time right there, and we have this equation down here at the bottom. All right, that's kind of the quick version of how this is formed. But this is the trajectory equation. Right here. Okay. And so we're going to use that in the next problem to solve for where a ball will be in the y direction given the x direction. And this is a field goal football problem, and of course it's Downingtown East, and 1 second left, down by 2 points, you need to kick a field goal. Okay. Well, our displacement, that is our x displacement, we'll say delta x is 36 yards, which is really 32.19 meters. Okay, that's how far away the field goal is, and he always kicks it at 50 degrees above the horizontal, so our angle theta is going to be 50 degrees. You can write north of east if you want, but that doesn't really matter. Okay, and what we want is we want the ball to go over a 10-foot, or that is a 3.05 meter crossbar. Okay, so I'm going to write this. I'm going to write our y final minimum. So at minimum, it has to be 3.05 meters above the ground when it passes the crossbar right there. And the question is, will it be at that or above that when it moves at 32.19 meters towards the field goal? Okay, that's the question. We're also told one thing in part A right here. We're told that the initial velocity is 19.65 meters per second. That's pretty specific, but that's what we're told in part A. All right, so we want to find where will it be? Where will the final Y position be? Or really, what is the change in Y when it reaches the field goal crossbar 32.19 meters away? Okay, so these are basically going to be the same thing because we're going to assume the ground is 0. So the change in Y, that is the Y location, and Y final is going to be basically the same thing. So let's use our range equation. Okay, we can say that delta Y equals our x displacement, right? That's 32.19 meters. Okay, times the tangent of theta. Tangent of theta. What's our theta? That's 50 degrees right there. All right, and then there's this whole other next part here. And by the way, this will test your calculator skills. So that's kind of one part of the expression there. So it's all that minus all this other stuff. Minus g, which is 9.81 meters per second squared. And by the way, if you put negative 9.81, that would be a plus out front, but just do it the way we have it in the notes here. Times our displacement squared. Okay, so that's 32.19 meters, that value squared. All that over 2 times our initial velocity, right? So that's 19.65 squared, right? And that all that times it says in the equation cosine squared theta. What that really means is cosine of theta, or cosine of 50, that value squared. Cosine of 50 degrees squared. You can't really put the squared next to the 50 because it would be cosine of 50 squared, whatever 50 squared is. We don't want that. We want the cosine of 50, that value squared. So that's why we put the squared on the outside of that big parentheses right there. And then we close the parentheses. All right, so all that, we have all those knowns, and this is our trajectory equation, and we can solve now for our delta y. How high will it be, that is in the y direction, when it has moved 32.19 meters horizontally? And if you key that in, and you're gonna have to get used to putting brackets in to separate out all your expressions, we're gonna find that our delta y, or our y displacement, is 6.5 meters. So hooray, our Downingtown kicker makes a field goal. He makes it quite handily. He's got about twice the height that he needs to cross the crossbar. So that's great. But part B asks us, if he wanted to just barely make it over the crossbar, the bare minimum that would get him get the height to be just barely what he needs, or the minimum 3.05 meters, how hard would he have to kick it? Or that is, what's the minimum speed? That's what this is saying right here. What's the minimum speed in order for the ball just barely to go over the crossbar? Okay, so for part B, our y displacement is the minimum. That's 3.05 meters. Okay, and let's see here. Everything else we pretty much know, but what we have to do is we have to solve now for our initial velocity. That's what we're solving for. So we need to take this equation, and we need to turn it around and solve for initial velocity. So I'm going to write the whole equation out. Delta y which we know now, that's our minimum, equals change in x times the tangent of theta plus g times the x displacement squared divided by 2 times initial velocity squared times a cosine of theta squared. Okay, that's our trajectory equation, and we want to solve for this right here. We want to solve for that. So what I'm going to do is I'm going to move all of this to the other side. Okay, so that's so delta y minus delta x tangent of theta equals g delta x squared over 2 initial velocity squared. It's getting crazy, I know. Times the cosine of theta squared. All I did was I moved this to the other side. Okay? And what I'm going to do is I'm going to take just our initial velocity squared and multiply it so it comes up. And I'm going to take this whole expression right here, delta y minus delta x tangent theta, and divide by that and bring it down here. So they're basically going to trade places. So that means that I'm going to start over here. Initial velocity squared equals g times delta x squared divided by 2 times all that I just brought down, delta y minus delta x tangent theta times cosine of theta squared. Alright, now to finally solve for initial velocity, we have to get rid of the square root right here. So we're just going to square root the whole other side, and then we'll solve for vi. So vi is going to be equal to square root of, do I really want to write that again? Yeah, I do. G times delta x squared divided by all this. And again, this also will test your calculator skills. 2 times delta y minus delta x tangent of theta minus cosine of theta, that value squared. If we can do that, and if we can plug in our values, all of which we know that the minimum initial velocity in order to get this ball to be at 3.05 meters when it is moved 32.19 meters horizontally, that will come out to be, if we plug it all in correctly, 24.75 meters per second. That's our initial minimum velocity if we set that height to be the bare minimum 3.05 meters to cross the crossbar. All right, so that's an example of the trajectory equation. Like we said, not as useful, not as handy as some of the other equations, but in the right circumstance, it'll give you exactly what you want. It basically returns a y value if you plug in an x value and you know the initial velocity and in the theta, the angle.